Hello, Voxxed Vienna. It's a great pleasure for me to be here again in this beautiful city. In fact, I can tell you that Vienna so far is my favorite city in Europe. So you have a very beautiful city, very nice place. So that's why I'm twice as happy to be here, because you have this great conference in a beautiful city. My name is Edson Yanaga. I'm a director of developer experience at Red Hat. My Twitter handle is @Yanaga. Just in case you want to follow me, I tweet a lot about DevOps, microservices, Java, software craftsmanship, and other stuff. And today I'm going to talk a bit about advanced pipelines for hypothesis-driven development, because we want to make a step further. I believe that we might have already overcome the discussion around DevOps and continuous delivery, so we might be able to take the next step further, more advanced pipelines. I'm also a Java champion and a Microsoft MVP, which used to be a weird combination, but these days, well, the word has changed a lot, but so far I think it's, as Google can tell me, it's a still unique combination. I don't know for how long. And since we're discussing, I have to have the discussion about DevOps and microservices, because I need to get to the point and why are we using DevOps tools and automations and processes, and why are we using microservices to be able to achieve something. And in the discussion about continuous delivery in the past 10 years, we've been discussing about continuous integration, how can we automate our processes to take some steps out of our way for us to be able to simply deliver software into production in a predictable way. So, but, and in all of the teams that I've been talking to about continuous delivery, and if everybody believes that continuous delivery is a good thing, and we want to deploy software in a faster pace, so, but I've always visited teams, and the number one excuse that they always give to me when why can't you deliver faster is that we can't deliver faster because every time we deliver something into production, we break things, which means that we have too many bugs into production. And since we have too many bugs into production when we make new releases of software, we need more time for testing. But people don't realize that the more time they have for testing, the more time they have to code, and the more they code, usually the more bugs they have. So instead of releasing software every month, they start to release every 2 months, and then later realize that we have even more bugs than we had before when releasing just 1 month. That's the traditional human way of trying to solve the problem of bugs into production, and that's the anti-economical way. We can do better. So the economical way of trying to solve these problems of bugs into production and trying to release things faster is trying to reduce what we call batch size. And technically the batch size in the DevOps world, to give you a complete scenario, I would say that bugs in production usually are caused by changes between each one of our releases. And these changes can be encompassed in 3 different areas. You can have changes in behavior, which means you change code. You can have changes in state, which means you change data. Or you can have changes in your environment, which is the servers or the configuration that you have in your environment in which your application is running. Okay, so technically, the batch size between each one of our releases is this amount of 3 things. I want to oversimplify this concept a bit. I'd like to say to you that what causes bugs into productions between each one of our releases are changes in code. So we'll oversimplify a bit. And the more changes in code that you have between each one of your releases, the more bugs you have into your production environment. So that's the human way of trying to solve that. The economical way is that instead of trying to increase the amount of changes, we're going to reduce the amount of changes between each one of our releases so we can have fewer bugs into production when we release software. Right? And why is that? Because we as humans, we need to improve the feedback loop in our software development process. And to be able to improve that, we need something called context. And for me, context is the amount of information and the amount of time that you can hold this information in your brain. Because we as humans, we are very good in establishing correlations if we have the right amount of context in our minds. So if I do something and I get this result, I'm very capable of establishing a correlation. Well, I did this, this went right, or did that, it went wrong. But if I have too much information in my mind, it's hard for me to establish context because, well, I changed a lot of things. How do I establish it? What thing in this huge amount did I change that led me to this result? So it's hard for me if I have too much information for me to establish a correlation. And again, if I hold this information for too long, like if I did something today and I'm only getting the result of these things into production 6 months later, it's very hard for me to establish this correlation. So for us to be able to deliver better software and safer into production, we need to have the right amount of context in our minds, the right amount of information, and we need to hold it only long enough for us to establish this correlation. That's why we need to reduce our batch size. That's why we need to develop software faster, and this way we'll be able to have fewer bugs into production when we release our software, okay? So that was the basic discussion about DevOps so far. So the main goal of all of this DevOps and microservice discussion that we had so far was to try to reduce the risk of releasing a new version into production. So if you're not yet into this step, like I think I already have a fully automated software deployment pipeline, maybe hypothesis-driven development is not for you yet, because you need to achieve this point, and that the risk of releasing software into production is very low. Up to the point that you can establish this correlation easily. I did this, I'm getting this result in production, and if I broke something, it's very fast and very easy for me to just spot the cause of the bugs, fix it, and release a new version into production. So teams that have sufficiently advanced software deployment pipelines, they usually don't even have a rollback strategy because it's much easier for them to just roll a new version forward, fixing the bugs that they just created into production. So that's the baseline that we have on the discussion about DevOps, continuous delivery, continuous integration, and something else. So far, we just aimed at reducing risk. Now we'll reach to the next step. And if you think about these continuous deliveries pipelines, traditional pipelines so far always focus on the next version. So a traditional pipeline could be seen like this. If I have like a version 1.0, I'm coding the next release will be 2.0, it will be better than version 1.0, it will have fewer bugs, it will have more features, and we will improve my business results. Then you start coding the next version, 3.0, which again will be better than the previous one. So your path between your versions is clear. You're always getting the requirements from your next version, you're coding and releasing that into production. So your trunk always goes forward. So this is a traditional pipeline. And making an analogy about traditional pipelines, you can think about traditional pipelines as if you have a restaurant, you have a buffet, and you have like all of the recipes for the meals that you need to cook. You just cook all of them and deliver that to production so your users or your customers can start to consume your food. But if you ever went to a restaurant, you can quickly check and assess that, well, some dishes people like more than other ones, so you have to keep refilling that recipe more often, while some recipes usually don't get consumed that often. For example, broccoli and other like nice stuff, usually they're left behind. I don't know if you guys are fans of broccoli or not. In Brazil, we're not usually fans of broccoli and zucchini and other healthy things, right? So you have some dishes that people leave behind and other that people prefer. So you have this imbalance, but still, if you're at the kitchen, you have to cook the whole recipe of broccoli or zucchini or eggplants and deliver that to the buffet, because or else you don't have a full release, right? You need to have all of the buffet fulfilled to get a successful software release, even if people are not going to consume everything, right? This is traditional software deployment pipeline. So when we're talking about hypothesis-driven development, we can think about it differently. So even if you're in the kitchen and you want to cook things to your users, to your customers, maybe when we're discussing about hypothesis-driven development, instead of trying to fill the whole buffet, you can just start to creating small plates, small dishes that you can deliver to your customers. And instead of having to trying to fill a whole pan with your recipe, maybe you can just give a trial to your customer to check if they want the food before you do everything. So if they don't want the food, you don't waste your time producing that recipe, right? You can quickly switch to another recipe that might be better appreciated by your user or your customers. So that's one of the analogies that we have when we're discussing hypothesis-driven development. And when we make this analogy, I'm pretty sure that you might be thinking in your mind, well, but how does that translate into code? And if you're thinking about the code, well, if I might have like 2 different things that I want to deliver to my user into production, and he or she might like one or dislike the other, the easiest way for us to think about how can we materialize this hypothesis into code is to create, of course, a branch. So the first strategy that we had to create hypothesis-driven development was, well, we have version 1.0. Now we want to access this hypothesis. I'm not sure if users will be happier with this feature or this other feature. The classic example that people give is like, if I change the color of a button, I don't know if I'll sell more if the button is red or if it's orange, which in my opinion is a very poor example, but it's nice for simplicity. Because most of the times the greatest improvements are in algorithms. So maybe you want to change your recommendation engine, or maybe you want another algorithm for processing something that will lead you to better results. But again, when you create 2 different hypotheses, A or B, you're not sure which one will be better into production. So maybe you just create A and B, you have 2 different branches of development, but version A didn't perform that well into production, and you want to go on with version B. So we have like 2 feature branches. And again, feature branching used to be the default way for you to perform what we call A/B testing. And so people believe that A/B testing is very similar to like blue-green deployment. Conceptually, in the server side, they might use the same architecture, but I think one of the main difference between A/B testing is that we are monitoring some behavior from our users and customers. We basically, blue-green deployments, again, blue-green deployment is a terminology from the DevOps world until now, and the goal of blue-green deployments was to reduce risk of releasing new software released into production. So I perform a blue-green deployment because the new version might fail. So we're not discussing about that anymore. We believe that our releases won't fail. Now we want to know which one will perform better. So we need to monitor behavior, and of course, I'm not talking only talking about the statistics about uptime, requests per second, or something. I want some behavior that is meaningful to my business. How much transactions, successful transactions per second, how much money I'm making per minute, per hour, per day. So this is some kind of behaviors that we want to monitor. And discussing about these pipelines where traditional blue-green A/B testing is not enough, I'm going to show you some advanced strategies that some companies are using to be able to achieve this hypothesis-driven development. First one is smart routing. So let me show you a small demo about that. Okay, you can see my screen. First, as I said, I think this DevOps discussion is over. And you know that this discussion is over when all of the knowledge that you have on this area is consolidated into the infrastructure platform. So as of today, we can have traditional blue-green deployment. This is a console, OpenShift environment. And if you want to create a blue-green deployment, you can easily. I have 2 different versions of my application running here. And if I want to create I call that dumb A/B testing, but there's no consensus on this terminology, so I'm just going to create a new route saying A/B here, And I'll say here that I want to split my traffic between blue and green, and I want that to be 50-50. So if I'm just going to create that, I have a route, and here's coming blue, but you might guess I hit refresh and it's always blue. That's by default OpenShift is sticky. So I get the new route here. Well, got a green, a blue, about another browser. Got a green, finally. So this is basic A/B testing, and I say it's dumb because basically what the infrastructure is doing for me is round-robin testing. It doesn't know anything about the client. It just gets one request, route to an endpoint, gets the other request from another client, and issues to another endpoint. We can improve that because if you want to be smarter, if you want to perform like great hypothesis-driven development, we need to be able to profile and segment our users. So let me close this. And for that, we need something. One of the strategies that we can use if we're using feature branching is to use smart routers. And with a smart router, basically you get your clients, you put a smart router in front of it, and you have two separate deployments with two different versions from two different branches in your backend, and your smart router will filter and segment the connections from your clients to the appropriate backend. So far, the most popular smart router that we have in the market, thanks to Netflix, is Zoo. So what I want to show you right now is I have a Zoo instance running here in my machine, and Zoo works basically like this. Zoo is a very simple application. If you dig into the source code, basically Zoo is an embedded Tomcat server with some libraries for routing, and it dynamically reloads your route configuration by default every 5 seconds. And all our route configuration is written in Groovy. So it's dynamic. It just pauses your folder every 5 seconds for new Groovy definitions. If anything has changed, it just reloads. It works beautifully on the Netflix infrastructure because they have a shared Cassandra file system. And when they write something, they change a new rule. This information is propagated through the cluster, and all of the Zoo instances they can pull the file system and update their routing configurations. So what I want to show right now, Zoo is running, but if you get here to see my route configuration, all of that I'm doing is that I'm just routing all of my requests to my blue deployment. So if I go to my browser and I try to access my Zoo instance, it will always return blue for me. But if I just go here and just switch here, I comment the code, I save the file, I wait 5 seconds for it to be reloaded, I just go back to my browser and reload, and it's green. Okay, forgive me, my machine is a bit slow because I'm running a lot of things. Later I'm going to show Istio, a service mesh, so I have a lot of things running on, so it's behaving a bit slow. So dynamically just change the routes, and okay, it's a very simplistic, again, example. But the important thing to think about Zoo here is that Zoo runs Java code or Groovy code in the application layer. So all of the knowledge that you have in your application layer can be applied here inside Zoo. So one of the nice things that people use here at Zoo, in fact, the other example that I had is like if you have mobile requests come from an iPhone, you can route that to a purple router. But as of today, even like dumb routing, like from infrastructure-based routing, can just get the headers from your HTTP request and route that to appropriate backend. A nice thing for you to add here inside the Zoo code is that I'm releasing a new version because I believe that our service is performing poorly for a certain segment of our users, and that the female users ranging from range 20, 25, that live in South America. I think we need to improve because they have a different behavior from my application. So we want to test this new version that I'm releasing specifically for these target users. You know, it's impossible for infrastructure to have this kind of knowledge, but since you're in the application layer, You just get the user that is logged in. You just get her profile in this case. You just point that to the new deployment that you're testing. Okay, so Zoo is just like a way for you to add some beautiful ifs in your routing rules to get to your appropriate context. And this is the most popular solution that we have right now when we're talking about smart routing, which again assumes that you're doing feature branch development, 2 different deployments of your application running into production. Now, but I have to tell you, be careful with feature branches, because feature branches enable back again one of the huge problems that we had in the DevOps world that we tried to solve with automated software deployment pipelines. We just get in everything back again. So, and why is that? Think about feature branching. When you develop, you have the trunk, which is the code that goes into production. And when you enable feature branching, which is very popular these days, because if you have a feature branch, you can just issue a pull request on GitHub or any other platform. So many people seem to like feature branches these days. But the problem if you're developing a project with feature branches is that, of course, I'm saying that you already have a fully automated software deployment pipeline, and you're using all the best practices for that. So even if you have a feature branch, you're constantly pulling the changes from the trunk to your branch. So like feature branch A and feature branch B, even though people are coding and committing to these feature branches, every single day or every single hour, people are pulling the changes from the trunk. Even you're not doing that, maybe you're not even doing that manually. Maybe your CI server is already doing that for you, right? It's constantly pulling the changes from the master, is already executing the build. So if any time somebody commits something to the trunk that would create a conflict in your branch, you get a broken build, and you are notified about that. So this is basically the best practice that we have with feature branches. But the problem with that is that when you're doing development in feature branch A and feature branch B, you're never accounting for the changes. If you're in B, you're never accounting for the changes that people are doing in branch A. You're just getting notified by the changes that people are committing to the trunk. So imagine that you have feature A and feature B. You just keep developing these features for like 2 weeks. You have a lot of different commits about that. And then somebody decided, well, we perform an A/B testing in production, and feature branch B is good enough to go to trunk. So we'll just finish trunk. Feature branch B is going to be merged to trunk. What have you just done when you merge your changes from B to trunk? You created a huge batch size which consists of 2 weeks of commits, and you deployed everything in just one time to your trunk. 5 minutes later, people developing feature branch A, they decide to pull the changes. And what do they have? A huge conflict. And in all of the teams that I've visited so far, when these kind of things happens, the conflict so huge, is such a mess that they don't even try to fix it, because it will take like 3-4 days, 1 week trying to solve the conflicts. They just discard all of the changes that they had. They get the feature branch, they see what did I change here, and they copy paste the code. Well, the copy pasting never sounds like a good approach, but that's what happens when the conflict's so big, because you just created a huge batch size when you merged all of the commits from feature branch B into the trunk. So this is one of the main problems with feature branches that we need to try to avoid. I don't know how many of you have ever tried feature branching development, but it happens quite often. It happens to me, of course, a lot of times, and that's why one of the reasons I don't like this kind of development. I prefer to advocate for trunk-based development, or if you still prefer feature branching, make sure that your feature branches are short-lived. Short-lived like 1 day or 2 days at most. It really depends on your pace of development, but make sure that they are very small so that your batch size can keep short. And when you merge your things, your trunk, you don't just screw everybody's life on that week, right? So feature branches, these are the dangers. So maybe we have another kind of approach for performing hypothesis-driven developments, and one of these approaches might be feature toggles. So feature toggles, again, is a very sophisticated name for dynamic ifing approach inside your code. So it's a very nice name, but the implementation is kind of easy. And with feature toggles, we are doing trunk-based developments, and we're trying to employ one of the goals of continuous delivery, which is we're trying to uncouple release from deployments, which means that traditional software deployment pipelines, releasing a new version of software or releasing new features of software every time I make a deployment. With feature toggles, we're trying to achieve the fact that we're issuing multiple deployments, and we dynamically can release the new features of our users, and we can roll back these features too at runtime. And how does it work? So I'm going to show you here a demo. First, let me stop my zoo instance. And I want to show here with code. Oops, here I'll exit this presentation mode. I don't need zoo anymore. Now I need this demo. So I created a very simple Spring Boot application using a feature toggle framework, FF4J, which, as far as my research went, is the most popular feature toggle framework being used in the Java world right now. So you use FF4J, is very simple, has a very simple configuration. All you have to do is just create an FF4J instance. If you're using Spring, you can just instantiate the new bean. You define everything in a XML file, ff4j.xml. And here you just declare, well, I have this feature called hello. It's enabled by default. I have the description. I have also another feature, which is a new recommendation engine, which is not enabled by default. And I have the description, which will be this description will be helpful when I have this information at runtime. So if I go back here to my controller, which uses FF4J, basically I just add FF4J for dependency with the dependency injection, and I get here a check. If ff4j.check this feature toggle, hello. If it's enabled, I say hello. And if it's not enabled, I say hello. Yeah, okay. Sorry for my German. So if I run this application, I can just get here and slash hello. I get my result. Okay, hello. So how do I change the information in runtime? Luckily for us, I can get here to ff4j console, which gives me this nice panel. I can go here to features, and you see, I can have these two feature toggles, and it's enabled by default. If I switch off the toggle, I go here to hello, refresh it. Well, it was a very, but now it's in German. And now it's the right way, right? So, and switch back, flip back, and we'll just say hello. It's a dynamic. By default, the ff4j is storing this information in memory. Of course, in production, you will use a database or an in-memory cache like Infinispan or Redis or something like that. But for demo reasons, it's just showing you here. But again, switching strings is a very simplistic example. Maybe we can show something more sophisticated. And what did I create? I created a recommendation controller, which basically, when you get a request to that, you have a bean of type recommendation engine, and returns to you your recommendations. So basically, when I want to test two hypotheses, I can just create another implementation of my recommendation engine interface. You see, it's just an interface. And if I go back here, for me to dynamically proxy this information with ff4j, I just have to say ff4j feature, new recommendation engine, And FF4J is going to flip the implementation for me dynamically on this controller. And how do I achieve that? I just have to go to my FF4J application. Here I have one instance, a default recommendation engine. I just need to create another instance, which is improved recommendation engine. Return new improved recommendation engine. And I declare that by default as a bean. If I run my application as is, Spring will complain that I have two beans implementing the same interface, so it's going to have a conflict. So I have to tell Spring, well, one of them is the default, and the other one is like a spare one, which is going to be used by FF4J. For me to do that, I just have to add a annotation, which is a Spring annotation. Primary bean is the default recommendation engine, and the other one is going to be used by somebody else. So I rerun my application here. And it's running real low. So if I go now to my recommendations, as you can see, I'm showing right now some default recommendations, which are very poor. They are so bad that it screwed my... Okay. So burger, soda, and hot dog, maybe you can improve this. So if I go to my FF4J console, and I decide that I want the new recommendation, turn it on, I just get here, refresh, and I get much better food, right? In fact, it's so nice that I've been here at Vienna for 2 days and already ate this 3 times. So it's really good. Yeah, you don't know how good it is until you're not from here. Okay. So that's how you dynamically change your beans using FF4J. And again, up to my knowledge, FF4J is the most popular feature toggle framework in the Java world, and some teams are using this successfully. But like everything in life, you have downsides for feature toggles. One of the largest complaints about feature toggles is that even though it enables you to have trunk-based development, you don't have feature branches. Everybody commits the code into trunk. Is that if you're using the if checks, you have like this distributed if checks spread all over your code. If people are using too many feature toggles and they forget to remove the ifs, you have a technical debt that you have to clean up later. So this is one of the complaints, and I've seen that myself in 2 of the teams that I visited, is that people don't realize that if you have like a large team and everybody's performing their hypothesis-driven development, in one team particularly I've just visited that, and where they were monitoring the production results and they were switching the toggles, and well, we get these results. We switch it back, we're getting another result. Then the next day they do the same. They monitor, well, we do this, we do that, and they get different results. They assume that, well, maybe it's the day of the week. Then they run that the other week, and they do it again, they have different results. What they realize is that in the whole team developing that service, you have so many hypotheses being tested at the right time, at a given moment, that you have like 40 feature toggles being tested at the same time, which meant that none of their monitoring was useful, because every time they were flipping the switch, you have like too many flips changed at the same time that you never get something meaningful in the end. So since they had a very large team, the solution for this problem for them was that nobody would be testing more than 2 feature toggles at the same time. But how do you do that if you have like multiple teams developing the same software? They had, unfortunately, to create what we call a feature toggle governance. They had to create another hierarchy of management, and this layer would say, well, now this week we are going to test these feature toggles, and that's it. Then the other week we're going to test the other feature toggles. So they needed to add like a governance to be able to schedule the feature toggles that they want to test. Not the ideal solution, but that's the way that they solved the problem so far. If you're using feature toggles and you have too many people messing around with the same code base, they added some layer of governance. And the other solution for this problem of trying to perform hypothesis-driven development is that today we can think about using a service mesh. I know service mesh might be a new concept for many of us. In fact, in this demo, I'm going to use Istio as the service mesh. As of today, Istio is not even production ready, but will be very soon because we have many companies investing on that. We have companies like Google, Red Hat, IBM, Lyft, and many other companies too, investing in the source code of Istio. So it will soon be production ready. So basically, I don't want to explain Istio because it's a long explanation, but basically what you can do if you have like lots of services running into your infrastructure, you can add some kind of layer for governance of the relation between each one of those services. So if you're concerned about distributed architectures, one of your concerns probably is tracing. You want to trace how a request comes from one node, goes to another node, then it follows, and when it comes back, how long did it take in each one of the nodes? And the traditional way of doing that is that you need to instrument each one of your endpoints to propagate the tracing information. With Istio, there are two different approaches for that. I'm going to describe only one. I'm going to describe the sidecar approach. You have the node proxy approach, but I'm not going to demo for you that today. So what you have as a sidecar approach is that if you're using a platform like Kubernetes, which has the notion of pods, and if you have in your pod, you have your application instance running, you can add another container inside the same pod, and this container will basically proxy all of the incoming and outgoing requests from your application. And what this proxy does, well, in the default Istio implementation, you're using an Envoy proxy, which is a project, open source project contributed by Lyft, which is very small, very fast. It's implemented in C++. And in each one of the instances of application, you have a sidecar container called Envoy. If you want to add tracing, Envoy intercepts the inbound requests, adds the tracing information to your backend. Then all the outgoing requests, Envoy again intercepts the request and adds the tracing information for your tracing server. So you don't have to change a single line of code. You just go to the Istio configuration and says, well, I want in all of the instances of my application to have sidecars that will proxy and add tracing information. This is one of the things that Istio can do, but Istio can also add like circuit breaking. A traditional way of doing performance circuit breaking is add the circuit break in your code. If you think about that, it's just a distributed try catch. That's the traditional way. Istio can add a distributed circuit breaking, can add retries, can add pull ejection, can insert faults. If you want to create your own chaos monkey, Istio can inject faults in your system to check how your system behave, how resilient is that. But talking about hypothesis-driven development, the feature that we're interested in the Istio implementation is mirroring, because we want to perform some hypothesis-driven development, but we want to play on the safer side. I don't want to release a new feature in production without assuring that it will behave very well without impacting my sales. Or even if I don't want to reach up to this point, I can like mirror my deployment and just check the statistics for this mirror deployment to check if I would have a successful output of that. And how does it work? So I want to show you first before discussing data. So if I go here to my OpenShift instance, I have like 3 different services: customer, preference, and recommendation. And I have 2 different versions. Here I'm using feature branching because I have 2 different deployments in my backend. I have recommendation 1 and recommendation 2. And sorry for this poor interface, but it's all text-based. And if I execute a curl here, you can see that by default, OpenShift will round robin my request between the two deployments. But what I want to, and if I decided to, let me increase, oops, my font size here. If I have two different implementations, what I want to show you today is that I have this guy. Let me check the logs, turn, recommendation. Okay, so if you can see the logs, I'm receiving requests. My counter is increasing, 62, 65, 66. And let me just stop here. I'm going to create an Istio rule saying that I want to mirror. I want to mirror all of the requests from my version 1 deployment to the version 2 deployment. So version 2 will be out of production. So all of the requests will go through version 1, and version 1 will produce the results that will go into production. But the Istio proxy, the envoy proxy, will generate a copy of the request, send this request to the version 2, and we'll forget. So it's a fire and forget approach. It just sends a request to version 2 and forgets about that. So this is what Istio does. So if I do this, I just created here. And if I curl again my service, you can see that I only get replies from version 1, but version 2 is still getting the requests. So requests are being sent to version 2, but I'm being, from the production point of view, all I get are requests from version 1. So this is the first thing that enables hypothesis-driven development with mirroring. So you might be thinking, how useful is for me to create a mirror if I don't get to check the results of the outcome of this new version 2? Okay, so what I'm going to discuss right now is like a bleeding edge, is what people are thinking about today, as what like many startup companies are implementing. First, the discussion is what about my data? Because I have a new production, new version, or two different versions running into production, and they're accessing the same database, the same data. How do I handle this if one of them might not be performing well, for example? So one of the approaches that you can do for that is that you allow both versions to be running successfully into production, and I've described some of the strategies that you can do with that in my book. So in fact, chapter 3 handles how you can have like two different versions of your application regarding to database schemas running to production successfully at the same time. If you want to get a copy of the book, it's in this URL or at my Twitter profile. But if you want to perform a further analysis of mirroring, is that I've done that before. Like you mirror a service, then what do you do to access the result of your new version? You just get your production database, you restore a backup in another instance, and this version 2 points to the copy database. Then you just check, well, you just open your database CLI or your application and check if the data is being written correctly or if it's giving the results that you would expect. The problem with that is that I witnessed myself is that creating this copy database takes a lot of time. I've worked like in an environment that it took me like 12 hours to be restoring a backup to be able to perform this kind of testing. And so it took a long time, and you run for some time. You check that well, and as the day goes by, the databases, they differ so much that by the end of the day, it's not possible for me anymore to assess if the data is being written correctly, because too many production transactions went here, and here I made some fake transactions too, so I can't compare in a meaningful way both data sets. So one of the solutions that we're trying to apply about that, is to add a virtualization layer. So you can, that's the proof of concept that we're working right now. If you add a virtualization layer like TEID you can create, you can have your production database, and you create an empty diff database, which will only have the requests, the results of the requests made in the and the version 2 application. So if you any inserts, updates, and deletes will only be recorded on the diff database. And in this way, you can get your requests. They can be processed on both backends. And if your new version is processing the request in a different way, you can just compare and see the results, because the diff database, if you query that through the virtualization layer, it will still contain all of the production rows plus the diff rows. So it's a much more efficient way for you to compare the data in both databases. This is one approach for you to solve the data problem. And another approach, which is like very new, there is a project that was recently released by Twitter, which is called Diffie. In fact, Christian Posta and Alex Soto, which just gave a presentation earlier this morning for you, they've written a blog post about using Diffie to compare different versions of your services running in production using mirroring. And basically what Diffie does is that even though you can't see the results of your mirrored instance into production, Diffie gets both results. It sends the request, it gets both results, and compares the results from version 1 and version 2, and then logs it into its database. So you can compare, well, version 1 is giving me this result, version 2 is giving me this result, and then logs it into its database. So you can compare the results of mirrored services. So this is another thing that is brand new. People are working on that right now. And another discussion is, what about my other services? Mirroring is simple if you just have like the final endpoint, but if you're mirroring a service that is invoking other services, the scenario gets more complicated. And the solution for that is many people are using service virtualization for that, which I don't think it's a good name for what they're doing. They are mocking like backend services in the mirrored service. I would prefer mocked services, but then I just realized that service virtualization was a term coined back in this SOA world. So it is a term that has like 15 or 20 years, and we're just reusing the same term here now that we're talking about microservices and service mirroring. Okay, and that's what I had to show you today. Again, most of the mirroring part is brand new. Feature branching with smart routers and feature toggle is something that people are already using in production. Mirroring is something that is being regarded mostly in startups and unicorns or companies like Twitter and Facebook, and this kind of which have like very mature deployment pipelines. But that's what I had to share to you. We're discussing all of these, and we're publishing a lot of this information in the developers.redhat.com website. And thank you very much. I don't know if we have time for questions, but if nobody kicks us out of here. What's the overhead of Envoy, and if I can use Envoy to monitor that part of me is outside connections like to other endpoints outside the cluster? Okay. By default, if you use first question is that how much is the overhead of Envoy? So in our test, Envoy has a very low latency. It's a very small sidecar implementation using C++, but it's a network round trip, right? So it's as small as it can be, considering that you have another round trip inside your own local host. Okay. And for memory-wise, I think Envoy consumes like 20 or 25 megabytes of RAM, which is pretty small compared to a JVM, but that's something that you might consider. If you have like 200 instances running to production, you have 200 copies too of your Envoy proxy. And if you're using Istio, by default, the security model of Istio and Envoy, Envoy blocks all outgoing connections to any endpoint outside your cluster. So if you want to allow your application to perform outbound requests to nodes outside your cluster, you have to go into the Istio configuration and ask Envoy to explicitly, I want to allow requests to this domain name or these IP addresses. So yeah, this is the way that you can do it today. Yes, you can use it as an outbound firewall application for anything because, again, Istio is agnostic of implementation. It's on the network level, so you can use it for Java, Ruby, C++, Python, PHP, anything that you want. Okay. Any other questions? Toggle Z? Okay. I've tested Toggle Z myself, but what do I say? I've only visited, I think, 3 teams that were using future toggles with Java, and all of them were using FF4J. And in my last project before joining Red Hat, I accessed some future toggle frameworks too. And at that time, was 2 years ago, our conclusion was that FF4J was a bit more mature. But I don't have I can't make a statement right now because I didn't look back at Toggle Z in the past 2 years. So I don't know if anybody knows the Toggle Z maintainer. Maybe it's even more advanced than FF4J. I just can't answer for that now. Any other questions? No? Thank you very much again.